Hello and welcome to my series of tutorials looking at different ways we can create 3D optical depth representations of gas density meshes using the freeware Blender 3D. I am an undergraduate summer student at the University of California, Santa Cruz. In these tutorials I will be using spherical mesh outputs of the 3D MHD code Fargo 3D developed by Pablo Benitez Lampe and Frederic Massey. I attach Fargo's website and primary paper in the description. I'd like to mention that Blender 3D has been used for visualizing Fargo 3D before in the form of models created from voxel cube data, such as this one, which are incredibly useful as well as beautiful. This work was undertaken by Matthias Garate under the inspiration of Brian Kent, and I attach a link to his wonderful tutorials below. It should also be mentioned that the community as a whole is catching on to the idea of three-dimensional optical depth models. And the techniques which I will show you are probably not the only nor the best techniques available. However, I hope they serve as a catalyst for you coming up with your own ideas for using Blender 3D for ever more interesting data representation. Please note that I will put all codes I create onto my GitHub account, which I also link below. So, without further ado, let's get started. So let's start off by opening Blender. And please forgive me for my very loud, very slow computer. It may take a little bit less time on some of your systems. So Blender is funded by donations, and that's how it's a free piece of software. It's usually used for creating Pixar-like animations, like artistic stuff, and I'd highly recommend doing that as a hobby. It's really quite a limitless piece of software, animations and everything. Okay, so to start off with, we want to get rid of this central introductory box, and to do that we just middle click in any area, any part of this dark grey area here. Okay, so to start off with, I'm going to put on screencasting keys. This means that you can see exactly what I press. So if I forget to say, then you'll be able to know. So to get rid of this menu, we just press N again. It's really useful in Blender to learn as many hotkeys as you can. I haven't learned enough of them. You can do everything from various menus that come out of the sides and everything, but you can't do it as quickly as you can if you know the hotkeys. So to rotate around, to sort of like rotate around a central point, pivot around a central point, we just hold on to the middle mouse button and move the mouse. We can see three assets here. We have a cube, which is the object. That's what we can sculpt and what we can change and what we can make into anything that we want. It's just a default starting cube. We have a camera, and the camera is what you take high resolution pictures or renders through. So if we go ahead and render, we can either press this and then render image, or just hit F12. We can see the cube here. So why is this side in shadow? Well, if we head back to our 3D view, we can see that there is a lamp here. And we can select objects with the right hand mouse button. That takes a bit of getting used to, but once you're used to it, it's fine. So the lamp is obviously casting onto this cube, and this side here was the one we saw shadow on, and as we can see, that's the one that's facing away from the light source, and that's why it's like that. Okay, so we can select things with the right hand mouse button, and then with the left hand mouse button we can change where the cursor is. So the cursor, if you're creating a new object, for example by pressing Shift A, if we want to add, for example, a sphere or a circle or something, then it will be added at the cursor location. So that's basically how the cursor works. So yeah. But for what we're doing, we're going to be doing a lot of scripting work, and through our scripting we'll be creating the object from scratch, so we do not need this initial cube. So we just press delete and confirm. Okay, so as I said, we're going to be doing some scripting. We're reading in data. We can't do it in an artistic way. We have to just do it through raw number crunching. So to get into the scripting setting, we just hit this and then scripting. And we still have the 3D view up here. But on the left-hand side, we have a Python interpreter. So if we hit new, we can create a new Python script. So you can just type in whatever you want. Okay. Oh, wow, that was quite interesting. So we want to create something that can visualize Blender. So before we create a 3D model, we have to create a two-dimensional mesh from which we can extrude faces from. Okay, so extruding. If you imagine you have a square, if we were to extrude a square, which is basically a single face on its own, a two-dimensional shape, we create a new two-dimensional shape exactly the same, but it's attached by its edges to the old two-dimensional shape. So if we extruded from a cube and we made it go into the Z direction, assuming that the original square was in the XY plane, then we'd end up with a cuboid shape, if that makes sense. So we're going to be using that. We're going to be extruding from a two-dimensional mesh to make our 3D model. So how are we going to do that? Well, we have a couple of scripts that we can use, which I'll be putting online. So I think the easiest way to do this is just to copy and paste. This is the first method which I'm going to show you. And this method is slow, but I think it's quite precise. This is basically Blender reading in the data, the Fargo data, directly. And there's no intermediate, there's no pyplot images involved. That will come in techniques which I'll show you in later videos. So let's just paste in here. So let's go through what we're actually doing here. So this is a program for reading it. Well, this is a program just for creating that original object from which we will create the 3D model. So we're importing BPY, and BPY, Blender Python, is the Python library for Blender. So it's how they talk to each other. We have all of our conditions of our mesh listed here. And one interesting one to note is the optical depth limit and the absorption coefficient. So we're creating a model based on optical depth looking from the top. So if we're creating a surface of constant optical depth, we need to know what that constant optical depth will be. And that is the variable optical depth limit. And absorption coefficient is basically is the scientific absorption coefficient. So if an intensity propagates through a medium, how quickly it will dissipate into that medium, how quickly the intensity will drop off. So to start off with, we're going to use BPY to center our cursor, because as I said before, new objects that we create will be created at the cursor, and we need to know exactly where that cursor is, because later on, with later scripts, we'll be selecting individual faces. So we need to know exactly where the object has been created, or otherwise we really can't do what we want to do. So once we've got the cursor centered, we create a circle. So as you know, in Fargo, it's kind of like a donut shape, the mesh. So the inside is taken out due to computational restraints, and we end up with this donut shape. So to start off with, we're going to put a circle in with triangular slices, with sectors. And we're going to have the same number of triangular slices as we have azimuthal zones. So we're basically putting in the azimuthal zones straight away. But we currently got a circle, we want a donut shape. So the way that we're going to do that is we're going to select our shape, we're going to extrude the face, and we're going to make the second face smaller. So the two faces that we create are not actually what we're going to use. We're going to use the edges which join up these two faces. And sorry, the faces which join up the edges of our two circles, if that makes sense. So we're creating that donut. So the only thing to do after that is to delete the excess geometry, so to delete the two circles, and we end up with our donut shape being left. Okay, so this isn't actually reading in anything, so let's go ahead and just run the script and see what comes out. So here we go, it's a donut shape with a minimum radius and an outer radius determined by our mesh conditions that we've inputted. So that's jolly good. Now the next stage, we've got our azimuthal zones. We want to create our radial zones. So what we want to do is do a loop cut, or several hundred loop cuts usually. So I tried to research this, but I've managed to find no way of doing this using the Blender Python terminal. The Python terminal in Blender does have a lot of problems, but I think they will be fixed in the near future, so I think it is still worth learning. So the way that we're going to create those radial zones is just to Shift R, no, not Shift R, Control R, and we can see this pink circle that's now surrounding that central donut hole. So now we want to scroll up, and we can see a variable here called number of cuts, and we want to make one less number of cuts than the number of radial zones we have. So for me it's 200, so we want to make 199 cuts, and then we left click and we left click a second time, and now we have a two-dimensional mesh that we can extrude from. And I guess I could do an example. So we're currently in edit mode, which means that we're playing with a single object rather than looking at how objects interact. We can pan by holding down Shift, and let's have a look at a single face. So we want to select a face, so we can do that. We press E for extrude, and then we can do it in the Z direction by pressing Z. So basically that's what we're going to do for every single one of these, and we could do it by hand, but I'd rather just do it by code if possible. Okay, yeah, so now we're back to where we are before. Okay, so now we're going to go ahead and save this. We're going to save this in the same directory as our Fargo data. I'm going to call it, well, I'm going to call it test 6. And it's important to do this just so that it knows which directory the Fargo data is in. There is also a small glitch with Blender that it won't actually register what's in its directory unless you restart it, so let's go ahead and do that. Where was it? Video. So here's test 6. So there we go. Okay, jolly good. So now we want to go for our second Python code, which is called extrude model. We want to copy, and we want to delete all of this and paste. This Python terminal has a lot of useful features, by the way. If we just bring in this, we have a nice menu here for finding and replacing, and making it look how you want and everything like that. Okay, so this is the main code, the code that actually creates the three-dimensional model out of our two-dimensional model. Okay, so let's go through it. All of this is the same. Oh, let's save, by the way. This is obviously reading in the data, so my data is called gas-dens 1000. You can call it whatever your data is. We're reshaping that data into a NumPy array. That makes it a lot easier to play with when you're using Python. So here we have a really simple function where it's the optical depth contribution through a length dz through a density rho and with a absorption coefficient kappa. So simply all of them multiplied together. Here's a slightly more complicated function. This is the den selector, and this is why it was so important we had to add our mesh at the center. So basically what we're doing is, first of all, we deselect everything because we're going to be selecting each one of these dens one at a time. I call them dens here, but I mean they're zones. We're going to be selecting each zone one at a time, so we want to deselect the last one. We calculate our AZ step, we calculate our radial step, and then we just step along to select each one. So basically we can put in a radial number and an azimuthal number, and we've indexed all of them in our mind, so we just we can iterate through them, and that's the important thing. So we're converting to Cartesian coordinates here, and we put the cursor over the position of the face, and then all of this bit is just literally selecting the face. Sometimes commands in this terminal get pretty complicated, needlessly I believe, but all of this is simply selecting the face. Okay, so now we have a function for actually extruding it. We have a failsafe here for if things go a bit crazy. It deletes the face if we have an extrusion length dz, which is ridiculously high. So basically it's just it's already been selected, so this is just extruding it by this length dz. So doing what I showed you before. This is a function for calculating the z-step. So as you can imagine, we're in spherical coordinates here, by the way, and the z-step, the step going upwards, is going to be a lot smaller, closer to the center than it is towards the outside. So that's simply, we're making a small angle approximation here, which is usually applicable to Fargo data. We're simply calculating what vertical width each zone has when we're calculating optical depth going through them. Okay, so now we go straight into the main loop. We have several counters. Here we're iterating through the radial and azimuthal zones. We're selecting the radial and azimuthal zones, doing some more counters. We've got a percentage here, so here's the percentage of zones that we've gone through, so we know exactly how close we are to completion. And then what we do is we iterate through the Z zones. So if optical depth is less than the optical depth limit, okay, so this is basically if we're iterating through, if we're not at the surface of constant optical depth yet, then we just make optical depth is equal to the optical depth plus the optical depth contribution through the length, through the Z step with the absorption coefficient, which we assume is constant over the whole thing, and through rho that comes directly from the data, from the NumPy array that I mentioned earlier. Okay, so if we've iterated all the way through and we get all the way to the end, which is when I is equal to nz minus 1, we just print there is no calculatable solid boundary. We keep a log of the number of fails, because this gives no data, so ideally we don't want too many of these, because it doesn't represent anything in the image. And in my case here, I've decided to delete those faces. So if nothing is encountered, if we don't get to that optical depth limit, then we simply delete the face. There is a hole in the mesh, which I think is, you know, a fairly realistic representation of what it is. Okay, so once we get to the optical depth limit, we activate this else. So then we just calculate what dz corresponds to that optical depth. I'm doing it based on just what z-zone it happens to get to that optical depth limit within, but you can use statistical analysis to make it more accurate and you know, get closer to what it genuinely is, but for now I think I'm happy enough with my small angle approximation and just stopping at the zone, because we have 40 collateral zones, which means that you can get a pretty good image out just by stopping at that zone. And then we extrude that z distance, and then at the very end we're simply going to print the number of fails, print the percentage of fails, and then we're going to print done. Okay, and then we'll have our model. So now, before we run this script, this is going to be a long script. There's no doubt about it. So we want to toggle our system console. And this means when you do a long script in Blender, Blender itself actually freezes. There is nothing that can be done about this at the moment. It freezes, and if you want to do stuff on Blender, you have to open a new Blender file. So because it's frozen, we still want to see what's going on, so we just open the terminal, so everything that we print on here will be printed onto the terminal. So let's go ahead and run this script. Okay, let's have a look at the terminal. Cool. So we have this error which is called in an invalid context. This comes from having to change from edit mode to object mode in the script. And you can get rid of this. It just seemed a bit complicated, but you would be able to get rid of this. There is a way of Googling it, but it is just, you know, I don't really see the point. So we can see the percentage going up. We're at 0.73% already. It's going pretty quickly. It does take a fair while, I've got to admit. Luckily there is one that I prepared earlier. So at the end it will show us that it's got 0.55% of the zones have been deleted, and that's fine. So let's change to object mode, and we can see that we have a nice bow tie shaped optical depth model coming from the top, and we can see a couple of gaps here for where that optical depth limit was never reached, but that's fine. And yeah, so we've got a nice model here. And if we decide, let's go ahead and try rendering it. So render image, and there we go. So we can see the slight shadows. If we want to accentuate those shadows, we can just move this lamp a little bit. So an easy way of moving the lamp is simply to get that out and do 0, 0, and let's put it about 1, and let's see what it looks like now. And this has got closer to a central source, so yeah, you can see the shadows really clearly. This is a really nice object, I think. It's I'm going to show you techniques in the future to sort of accentuate the features closer to the star. It's really simple. And I'm also going to show you how to color this model, but that should be enough for now. I think it's quite pretty. You could even create a little 3D printed model of this and keep it on your desk. That's definitely something I want to do if I manage to get a 3D printer. So yeah, I've got a nice little pastel, and it looks lovely. So thank you very much for listening to my first video, and I hope to see you soon for the next one. Thank you.